All right, so first lecture quiz is not today, it's Wednesday. I have it right here though. Or that'd be the 14th. All right, last time I introduced all the 2D joints, and so today I just want to do some problems. I want to put some problems up, let you have some time to think about it, talk to each other about it, and then I'll go through them, make sure that what you're thinking about is the right way to think about it. So these are problems in 2D statics of rigid bodies. So the first one, you have a pin joint over at the wall. You have a circular mass with a diameter of 1 meter. This mass is 100 kilograms. And it's supported by a cable at the other end. Calculate the external loads on this mass. Okay, so yeah, just take a few minutes, work through this. Be sure you draw the free body diagram. Ask me questions if you get stuck and you want a little nudge, or talk to the people around you. And then after you've had some time to work on it, I'm going to go through it all, and you can compare your notes to, and you can sort of compare the direction that you've been going to what I do here. So first, free body diagram. So anytime you use Newton's second law or the moment equation, you need a free body diagram that corresponds to it. In simpler problems, it's not always super clear why it's necessary, but as problems get more complicated, you'll see like, yeah, I'm glad I built that habit, Okay, so there's the body. There's a weight force of 100 times 9.81, so 981 newtons down. There's a cable force that acts parallel to the cable away from the body. And then there's a pin joint. And what are the loads that a pin joint applies? This is the joint we'll use the most. So it allows rotation, but doesn't allow any translation. So it's a full force vector and no couple. I'll just call that R. Okay. We have 3 variables. I think that's all, yeah. 3 variables. We're going to get 3 equations because it's a 2D problem. So we should be able to solve it unless there's some like redundancy. So now from here, we can go to the table, row, force, moment. And we have to decide what our about point's going to be. Probably the way that makes it simplest is to put your about point at that pin. But it doesn't change anything about whether the problem's solvable or not. Just really in this case, I think it's going to let us solve it easily by substitution instead of using reduced row echelon form, but it's not a big deal. Okay, so first, the force R. What's the row vector from the about point to where that force is applied? This is the easy one. Whoever answers this one doesn't have to answer the hard ones as we go. Yeah, very good. Yep. Now you don't have to answer any more questions, and all these other poor suckers have to answer the hard ones. Force vector. Yep. And cross product, we're talking about a z component of a cross product. 0. Yep. And then the weight. What's the row vector? So from the about point to where that weight force is applied. Yep. And the force vector is 0, negative 981. Cross product is negative 490.5. And then the cable force, what's the row vector for that? 10, yep. The force vector. That's right. And the theta in this case is just going to be that 60 degrees. So t times cosine of 60, t times sine of 60, that is 0.5 t, 0.866 t. And the cross product is 0.866 t. And now Newton's second law, add up all those forces in the middle column, set it equal to 0. The moment equation, add up all the moments in the right column, set that equal to 0. If you want to take a step and write it out as a vector equation, that's perfectly fine. I'm going to just jump right to the components, to the individual equations. So we have Rx plus 0.5 t is equal to 0. The second equation, Ry plus 0.866 t minus 981 is equal to 0, so I'll move the 981 to the other side. And then the third equation, the moment equation, says 0.866 t minus 490.5 is equal to 0. So I'll write that as 0.866 t is equal to positive 490.5. So from equation 3, we can calculate t right away. What's 490.5 divided by 0.866? .566 point what? Okay, newtons. And I guess that means that Ry is equal to 14 what is it, 1471.5. And then our x is negative 283.2. Did I do that right? Okay, so now if you wanted to put this in a free body diagram again, the external loads on this body are a force vector on the left side of negative 283.2, 1471.5, and a weight force of 981, and a cable force of 566.40. Any questions about that? If you have, like, you already know the direction of it, you can just write it as a magnitude like that and just show the direction. I chose that. Okay, yeah. So yes, if you choose your about point to be where you have the most unknown, where you have the most unknown forces acting, it pretty often will sort of decouple the equations, and instead of having to solve it as a system of equations, you can just solve for the first variable and then plug it into the second, like it did here. But it's not an urgent concern, because you got your calculator right there. It's pretty easy to just plug stuff into RREF. But yeah, that's why I chose that, because the most unknown forces were acting at that point. Okay, second one. Yeah.
The diameter was then unnecessary information?
No, it was necessary for coming up with those row vectors.
Oh, that's right. Okay.
Okay, now this time we have a cantilever beam that's connected to the wall by a fixed joint on the right end. This beam has a length of 0.25 meters. And there's a force of 1,000 newtons applied at the left. And this angle is 30 degrees. And the mass of this beam is 3 kilograms. So calculate the external loads on the beam. So start with the free body diagram. there's the 1,000 Newton force, the weight force, 3 times 9.81 is 29.43. And then the only other loads are coming from the joint. This restricts all translation and all rotation. So in 2D, that means we have a full force vector, call that R, and a couple, call that MR, reaction moment. And I'm going to do the same thing with the about point I did before, put it right there with unknown forces. And now I'll fill out this table. So first, the force R, the about point, the row vector is 0. Force vector is Rx, Ry. Moment is 0. Second, I'll do the reaction moment. For a couple, we don't care about the row vector or the force. I mean, we would care about the force, but it's always 0 because that's what a couple means. And the moment is just the variable MR. And then the weight force, the row vector is negative 0.1250. The force vector is 0, negative 29.43. What do you get when you multiply those two? 3.68. The whole thing is 0.25 and the weight is acting at the middle. Yeah, so it's half of that. And then the 1,000 Newton force, that's the one that has a row vector of negative 0.250. And since this is at a 30-degree angle, so this is going to be 1,000 times cosine and sine of some angle theta. That angle theta in this case would be 150 degrees. And you would get negative 866, positive 500. And the cross product is negative 125. So now the equations, the x component of Newton's second law says Rx is equal to positive 866. The y component says Ry is equal to negative 500 plus 29.43. So that is negative 470.57, right? And then the moment equation says MR is equal to 125 minus 3.68. So that's positive 121.32. And it's already solved for us. So if you put this back into a free body diagram, you get a force vector of 866, negative 470.57. A couple of 121.32 Newton meters. I don't know, I usually just write the units so I can keep the forces and couples separate. Those are different things physically. And then you got the weight force down of 29.43, and then the force vector of 1,000 newtons. The theta, oh, for this one, so we did use it. We needed it to come up with the force components of negative 866, 500. But then when I put it back in the free body diagram, I just put it back as a magnitude because we know that direction. But you could also put it in as a full vector and put the components in, and that would be perfectly fine. Really, probably it's more useful to put the components in because you're going to end up using those if you calculate internal loads or something, which we do later.
Where did the negative 470 come from?
That was so when we added up the y components for Newton's second law, we got Ry minus 29.43 plus 500 is equal to 0. And so 500 minus 29.43 is 470.57.
Like just intuitively, that consider every force acting in that y-axis. There's the upward force from the cable, the downward force from the weight, and then some value to get to 0 from that velvet joint.
Right. So yeah, that's what's going on. Like those forces all have to add up to be 0, and so that takes a downward force of 470 just to zero it out.
Okay, yeah, I got it.
Any other questions about that one? Okay, let's do one more. I'm just going to do this one because we're getting short on time. But I want you guys to think about the angles on this one with me because the angles are going to get a little funky. That's good. That's a good habit. Okay, so we got this beam that makes a 45-degree angle with the horizontal. And at the upper right end, there's a pin that slides in a slot. And this slot makes an angle of 10 degrees with the vertical. This beam has a length of 2 meters. Oh, and there's an external couple too. That's so the only externally applied load besides the weight is this couple of 1,000 Newton meters. The length of this beam is 2 meters. It's at an angle of 45 degrees with the horizontal. And its mass is 40 kilograms. And we want to calculate the external loads.
What with these examples? Is there like a physical object that you're imagining?
Yeah, I pretty much just imagine that same beam over and over again in different orientations. Okay, so dealing with that pin and slot joint is going to, that's going to take a little thinking, figuring out the angles for this stuff. So free body diagram. We have a pin joint here. So I'll call that RA. That's a just unknown force vector, no couple. And there's the applied couple of 1,000 Newton meters. Then there's the weight of 40 times 9.81. So that's 30, what's that, 39.2. What is it? 392.4. And then up here, okay, so what's happening in the pin and slot joint? That's like that's the highlight of this example. So remember that a pin and slot joint, well, it can slide along the slot, so there's no force there. It can't slide, it can't move perpendicular to it, so there's a force perpendicular to the slot and no couple. So a pin and slot joint applies a force with a known direction perpendicular to the slot. And so if I have the slot drawn here, we know that the force vector is perpendicular. How did I know that the force was this way and not 180 degrees from it? It's a trick question, because you don't know. It doesn't matter. You could choose either one of those and the numbers will come out, and if it comes out negative, it's like, oh, it was the other way, But it works perfectly fine no matter which of those two perpendicular directions you choose, okay? I'll call this RB. Arby's. I'm thinking Arby's. Is that still a commercial? Is that still a restaurant? So we know the direction of that force. I drew the arrow, and so the variable associated with it is just a scalar. All right. So now the table. I suppose I'll choose my about point down here. Okay, so let's get the easy ones out of the way. There's no row vector for the force RA. The force is RAX, RAY. Cross product is 0. The 1,000 Newton meter couple, we don't care about row vector or force. That's clockwise in the XY plane, so that's a negative 1,000. Then we have the weight force. The row vector is, so it's, the whole thing has a length of 2 meters. So the midpoint is 1 meter away. The angle is 45 degrees. So that row vector is 0.7071, 0.7071. Why do I put in the extra digit? I don't know. I don't know. I just like it there. The force vector is 0, negative 392.4. That's cosine of sine of 45 times the length of, or the distance of 1. Yep. And can someone multiply that out? 0.707 times negative 392.4. 277.47. Okay. And now the only thing we have left is the hardest part of this problem, coming up with the angle for that pin and slot joint. The row vector is 2 times cosine and sine of 45 degrees. So 1.414, 1.414, I guess 2. Okay, now the angle. So we're going to have RB times cosine and sine of some angle. So how do we come up with that angle? Well, this is the way I always do these, and I like it. I think it works really well. So let's draw a vector. It could be either vector that's parallel to that slot. Okay, so there's one. Okay, and we know that this angle is 10 degrees, right? That's what's given. And then we know that the vector we want is perpendicular to this. So that's a 90-degree angle, okay? And now to come up with the angle for that black vector, the one we want, start at the positive x. It's 90 degrees to get to y. It's another 10 degrees to get to the red vector. So if we're trying to come up with this theta, our theta is, this was a counterclockwise rotation, so positive 100 minus 90, and we end up at 10 degrees. And so this is RB times cosine and sine of 10 degrees, which is, I think that's 0.9, oh boy, I used to know these, 0.9, what's 85? 0.985 RB, and then 0.174. 0.174 RB. And now that cross product, you're going to want to just plug that as a cross product into your calculator. Can someone calculate that and tell me what it is? Negative 1.59, and don't forget this is all multiplied by RB. Okay, so now the rest, I mean, we're out of time. I'm not going to finish it, but the rest is just taking the equations you have here. These add up to 0. These add up to 0. You have 3 equations for 3 variables. Okay. All right, so I'll put it on D2L2, but we have our first quiz on Wednesday. And let me know if you want to talk over Zoom, or I also have office hours in the tutoring center today from 1:30 to 3.